Yes.
Yes, sir.
Yes, sir.
Okay, thank you. So we were looking at graphs, and I think today and in the next lecture on Wednesday, we will be covering on trees basically. So today I'm going to finish few basic things about graphs. Some of these things you might be knowing from other classes, but anyway we need to complete the stuff. So I'm going to talk about it. So I already gave you some basic idea about graphs. So graph is collection of points and lines, right? And so what set of vertex, set of edges, such that we connect the edges. So we connect the vertices through edges and so on, right? So now I'm going to talk about one special graph known as bipartite graph. Okay. So bipartite graph is a very special kind of graph which is quite useful in in a lot of applications in decoding different kind of codes and so on. Especially Tanner graph is one of the such a bipartite graph known in engineering. So what is the definition of bipartite graph? Suppose G is a simple graph, okay? Okay. So if we can partition the vertex set of this set into two such set, disjoint union, right? So this dot means disjoint union. That means there is nothing common between V1 and V2. We partition the vertex set into two vertex set V1 and V2 such that every edge in the graph connects a vertex in V1 and a vertex in V2. Okay. So that no edge in G connects either two vertices in V1 and two vertices in V2. So basically this is V1 and this is V2, vertex at V1, and every edge in the graph connects a vertex in here and a vertex in here, right? Something like that. This kind of things are not possible. Okay, the vertex here connects to another vertex here in the same set. This is not possible. Okay, so such kind of arrangement is known as bipartite graph. So V1 V2 pair is known as bipartition of the vertex set. Okay, so V1 V2 is known as bipartition of the vertex set. So of course you will ask for what are the examples of such bipartite graph. So you remember we have the cycle graph C6, right? The last class we covered cycle graph. So I can partition the edges of the cycle graph like this. It has total 6 vertices. So I'm just looking at odd vertices 1, 3, 5, and V2 has 2, 4, 6 even vertices. So I can say this is V1, V2, V3. Sorry, V1, V3, V5, and then we have 3 vertices here: V2, V4, V6, V2, V4, and V6. Right. So this is one edge. This is another edge. This is another edge. This is another edge. Okay. This is another edge, and this is another edge. You can see that so from V1 you can go to V2, then to V3, then V4, then V5, then V6, right? And then from V6 you can go to V1 back, right? So this is a kind of cycle. So C6 is a bipartite graph. Right? And so can you give an example which is not a bipartite? So K3, complete graph on 3 vertices, is not bipartite, is not a bipartite graph. So that you can verify. Okay. So verify over a cup of tea in the evening. I think today tea time is over, so maybe you can do it tomorrow. Right? Now there is a nice characterization of bipartite graph. So remember, so bipartite graph, a graph is bipartite if you can partition the vertex set into two vertices v1 and v2, two set of vertices v1 and v2, such that every edge in the graph connects a vertex in v1 and a vertex in v2. So now there is a characterization, and this characterization is pretty common. I call it as a theorem. A simple graph is bipartite if and only if it is possible to assign one of two different colors to each vertex of the graph, so that no two adjacent, this is very straightforward definition, you know, or condition, to no two adjacent vertices are assigned the same color. Right. So we say that a simple graph is bipartite if and only if it is possible to assign one of the two different colors, you know, two different colors, each vertex of the graph. So I'm just coloring the graph, you know, each vertex set I am coloring. So maybe say one vertex I am coloring with blue color, another vertex I am coloring with red color. Okay. So, but if we do this and such that no two adjacent vertices are assigned the same color, then of course graph is bipartite. You know, I can sort of stretch it to create a bipartite graph out of it, right? So this condition is if and only if, right? So how do we prove that? The proof is very simple actually. First, this direction. Suppose G is equal to V comma E. So some vertex and some edge set is a bipartite simple graph. It's a bipartite graph, and you know, and suppose V is nothing but V1 disjoint between V2. Of course, where V1 intersection V2 is phi. Nothing is common. Okay. Then every edge. So it is given that the graph is bipartite. Then what we can do? By definition, every edge in E connects a vertex in V1 to a vertex in V2, right? This is by definition of the bipartite graph. Once we are able to do this, we will color all vertices in V1 with one color and all vertices in V2 with another color, and so we are done, right? So that means we are able to do this color business, you know. On the other hand, suppose it is possible to assign two different colors such that no two adjacent vertices are of same color, then we can partition V1 as set of vertices with one color, and V2 is set of vertices with other color, right? And so then of course V is equal to V1 union V2, and they are disjoint. So V1 intersection V2 is phi. By definition, G is a bipartite graph, right? So this is a straightforward proof. Any question at this point? Any questions? Please do ask if there is any question.
Sir, is there exist Tripartite or four-partite.
I mean, yes, you can generalize the definition. Yes, you can do the generalization. Uh, in fact, bipartite graphs are quite common, easy to study, and I think we are only looking at bipartite graph in the course right now. Okay. So now I will give you some quick examples. In fact, I'll give you one example where the graph is bipartite. So you see that if you have this, A, B, C, D, E, F, G. So suppose there is a vertex like this, A to C there is a vertex like this, B to F there is one, A to F there is one. Okay. And we have E to D there is one, D to C there is one, A to C is there already, B to C there is one. Okay. There is one also from B to E. F to D there is one. F to D there is one. E to B is there. Then G to D there is one. And A to E there is one. Okay. So this is a configuration. Now what we do, this is a graph. This is our graph, given graph. I want to check whether this is bipartite or not. So what I do, I will use the previous theorem. I'll start assigning different colors. So suppose I assign one color here. So I assign A as red color. So I assign A as red color, right? A as red color. So once A is assigned red color, so what A is connecting? You can see that A is connecting G, F, E, and C, right? So this, and this. These four I need to assign different color. If this is assigned red color, all these vertices will assign blue color, right? So all these tick ones I will assign blue color. Once we are done with this, okay, if these are blue, then of course B will be red, right? So I can assign this to be a red color. Okay. So basically this implies that B and D, these two will be red color, right? If we do this, so basically A is anyway red color. So you can see that we are able to partition it. So three vertex in one set. So V1 is A, B, and D, which is red color, and V2 is C, E, F, G, blue color. Okay, so we can do the partition. If we are not able to do this partition, if some vertex is left somehow, then there will be a problem, right? Or if we start doing this and it turns out that two adjacent vertices are assigned same color, there may be pictures like that. In that case, that graph is not bipartite, right? I think I leave it as an exercise for you. Find a graph which is not bipartite. This is an exercise for you, right? Find a graph which is not bipartite. Okay, so I think this is something you can do it. It's really straightforward. Now I'll give you another definition of what is known as subgraph. What is the idea of subgraph? Suppose G is equal to V comma E is a graph, then H is equal to W comma F is a subgraph if W is subset of V and F is a subset of E. Right. So basically, a subgraph H is proper subgraph if H is not equal to G. Right. I mean, if they should be different. Let us take an example. We have 1, 2, 3. Right. So A, B, C, D, E. We have here. Okay. This is a graph. So you can clearly see that this is a complete graph with 5 vertices, right? And a subgraph of it, H, I can draw A, B, E, B, C. This is a subgraph. I'm just taking certain vertices and edges as a subset, right? So this is a subgraph of G, right? Similarly, we can define union of two graphs, union of two graphs. If G1 is a graph, let us see A, B, and here I am drawing C, A, B, C, E, D. This is a graph G. And suppose I have another graph G2, which is A, B, C, F, and D. Okay. This is also D. So in this case, I think this is also okay. Union, I can, what will be the union of these two graphs? Union will be simply, I'll just draw. So basically, union graph, if this is G1 is basically V1 comma E1, and G2 is V2 comma E2. So we know that the union graph will have V1 union V2 comma E1 union E2, right? That kind of thing. So here it will be 1, 2, 3, 4, 5, 6. A, B, C, D, E, F. This, E, here. You can see that this is the union of two graphs, right? This is another operation that we can define on the graph. Now I'm going to give you 3 very important representation for the graphs. Like a graph can be, so basically I cannot keep on drawing these kind of pictures on the paper. If I want to deal with them algorithmically or through computer programs, I require some sort of data structure. How do we store these graphs? So there are different ways we can actually do this. There are 3 ways actually, essentially. So I'm going to give you representation of graphs. The first one is, adjacency list. What is adjacency list? It's something very interesting. You see. So if suppose we have a simple graph A, B, right? C, D, E. This is a graph. So what is adjacency list? I use write down the vertex, each vertex A, B, C, D, E. All vertex I have written. And for each vertex, what are the adjacent vertices? I should look at. A is adjacent to C and E and D. We have B, C, and E, right? And then B is A. C is A, D, and E. D is C and E. And E is A and C and D. So basically, this kind of list is sufficient to represent the graph, right? From this list, I can go back and draw this picture easily. In the space, I draw these vertices and they connect the things accordingly. What is adjacent to what, right? So this is known as adjacency list of the graph. So this right now, I have drawn the picture for this undirected graph. Same thing can be done with the directed graph as well. So I am just leaving that as an exercise for you. For directed graph, what happens actually? You will have initial vertex and terminal vertex. You can adjacency list will be initial vertex and terminal vertex where things are ending, and you can draw the things, right? Next, second representation is adjacency matrices.
Sir?
Yes?
Sir, for previous method, adjacency list,
Yes.
in a directed graph, we will have only that number of adjacent, means adjacent vertices, which will be equal to number of edges, right? And
No, so
in
initial, so it all
undirected graph, we will
no,
have two times.
no. What happens? It all depends what kind of graph it is. Suppose the graph has graph may not be simple as well. There may be a loop on a vertex, right? That might be a possibility. So I need to cover everything. So what I'm saying that I can, on one side I can write down all the vertices and I will call them initial vertex, right? Initial vertex, right? And then I write down final vertex. So that means it is telling me if I'm writing final vertex, there is an edge, there is a directed edge from A to B, A to C, A to E, right? So wherever there is a directed edge, I am listing them. Okay.
Okay,
Got it?
sir. Yes, sir.
Sir,
Yes.
sir, can the subsets W and N can be null?
Which subset here?
Yes. Subgraph, yes. W and N.
Yeah. Well, I mean, that will be a trivial subgraph, that will be a trivial subgraph, right? Because phi will be subset of everything, right? That will be
Yes.
trivial subgraph. Yeah. Okay. So adjacency matrix. So let me give you an example. I think this is also quite, I would say that actually I should say that which one we should use. So basically adjacency list is very useful when G is a sparse graph. What what is a sparse graph? So simple sparse graph, then we use adjacency. It's easy to use adjacency list because when when it has less number of edges, then adjacency list is very useful. For simple sparse graph, sparse graph means less number of edges. Then it is easy to manage. Otherwise, it will be difficult to manage, right? So if number of edges are more, then we use this adjacency matrix. When G is a dense graph, it is known as dense graph. When more number of edges. Okay, so how do we do this? Let us look at adjacency matrix. So A, B, C, D. These are the vertices. A is connected to C and A is connected to D. Suppose this is our graph. So how do we write down adjacency matrix? I form it like this. A. So of course, vertex set is A, B, C, D. 4 things, right? So I write down A, B, C, D. And I write down on the left side. So I'll try to form a matrix here. A, B, C, D. Now I ask a question: whether A is, connected to A itself, right? I mean, there is no self loop here, so it is 0. Is A is connected to B? Yes. Whether A is connected to C? Yes. A is connected to C here, right? Whether A is connected to D? Yes. Right. I'll put 1, otherwise 0. So this is 1, 0, 1, 0, 1, 1, 0, 0, 1, 0, 0, 0. This is very easy representation of the graph, right? So, okay, so one can ask a question, and I think I'll ask you the answer. When does A is a symmetric matrix? Symmetric matrix, you know, that means when A is equal to A transpose. For what graph? For what graphs G we have A is equal to A transpose? The adjacency matrix is the same thing as its transpose, right?
When the graph is
Sir, for all.
undirected.
Yeah.
Yes. Simple graphs, actually it is symmetric, right? So basically, if the graph is simple, then yes, right? So for simple
Yes.
graph, right? For simple graph, right? So I think you are understanding everything, which is very good. Because I cannot see your faces, so I don't know whether you are understanding what I am saying. But yeah, I hope that's good thing. Good sign.
Sir,
Right.
for a directed graph, what should we consider? Means if we should consider that row element is initial element and column
Yeah. So
element is final.
see, there are all kind of representation in the adjacency matrix. There are all kind of variations are also there, right? So it all depends. If there is a direction, so we can read it as our rule will be if there is a direction, we'll put 1, otherwise we'll put 0, right? That is also a possibility of doing. That way it will work in the same manner. Okay. So
Yeah, okay.
yeah. Now I think I would like to tell you one very interesting thing. Third representation is, so first one was adjacency list, and this representation is used when the graph is sparse. Sparse means when the number of edges are less, right? That means, then we use this. If graph has more number of, so basically if more number of edges means number of ones are too much. So then we use adjacency matrix. And third representation is incidence matrix. Incidence matrix, right? So I'm looking at undirected graph. Right. So let me give an example here. And I think that will be clear to you. Suppose this is V1, V2, V3, V4, and V5. We have an edge here between V2 and V3. Here, there is an edge here. There is an edge here, V1 and V5. V4 and V2 is an edge, and there is an edge here. So I can rename these edges as E1, first edge. E2 is second edge. This is E3, third edge. E4, E5, E6. All 6 edges are there. So here the matrix is a little bit different actually. This is vertex cross vertex cross edges. I make something like this. Okay, so E1, E2, E3, E4, E5, E6, and then 1, 2, 3, 4, 5. These are vertices, 5 vertices and edges. And I ask a question. So vertex 1 is incident to how many edges? So vertex 1 is incident to E1 and E2, right? So E1 and E2 there is 1, and all other places it is 0, right? And I ask vertex 2 is incident to how many edges? You can clearly see that vertex 2 is incident to 4, 5 and 3. 3, 4, 5, right? So basically vertex 2 is, yeah. So I can write down 0, 0. Vertex 2 is incident to third, fourth is there?
Yes.
4 and 6.
Yes, sir.
4 and 6.
4 and
And
6.
6. Fine. And this is 0. So basically you can complete 1, 2, 3, 4, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 0, 1, 1, 0. This is the incidence matrix, right? So this is also used, with the representation of the graph, So now, so these are the 3 representations of the graph. Now I'm going to tell you something very interesting. It is known as isomorphisms of a graph. Whether 2 graphs are, structurally same. Essentially, I'm asking this question. Okay, so let me show you some examples first. Look at this example here. G is a graph, vertex set this and this, and H is a graph, W and F, right? So I'm just writing 4 vertices are there: U1, U2, U3, U4. So this is something simply a square here, right? And this is V1, V2, V3, and V4. And here it is something like this. So now look at these graphs. I would say that, and of course, this is connected here. I will say that these are isomorphic. What do you mean by isomorphic? So I can actually twist this V2 and V4 actually, right? Twist that and the structure will be same, right? In other words, what I am saying that there is a function f from G to H such that f of U1 is equal to V1, f of U2 is equal to V4, f of U3 is equal to V3, f of U4 is equal to V2. And this function is 1-to-1 and onto. So if there exists a function which is 1-to-1 and onto between 2 graphs, between 2 vertex sets basically, such that the structure is preserved. What do you mean by structure is preserved? That means if U1 and U2 is basically connected, so then we know that the corresponding f of U1 and f of U2 will also be connected, right? Or adjacent. So essentially, here is the definition. We say that 2 graphs are, isomorphic. So we say that G1 and G2 are isomorphic. Isomorphism. Isomorphisms are basically functions which preserves the structure of the graph. So G1 and G2 are isomorphic if there exists a 1-to-1 and onto function f from V1 to V2 with the property that if A and B in V1 are adjacent, in G1. So if two vertices are adjacent in one graph, their corresponding images, if and only if f of A and f of B in V2 are adjacent. Got it? In G2. And this should be true for every A and B in V1. Any question at this point? This is very important concept. Graph isomorphism. Any question at this point? No question? So this is an example of two graphs which are isomorphic, means they are structurally same. Now I'm going to give you another example where the graphs are not isomorphic. So let us take another example here. So we have A, B, A, B, C, D, E. A, B, this, right. And suppose there is another graph A, B, C. We have A, B, C, E, D, and this. Can we say these two graphs are isomorphic? I would like to hear your answers. Can we say that these two graphs are isomorphic?
No, sir.
Why?
Sir,
This is G.
sir, we
Here
cannot
E and
find
D
that
and
Huh? So I would, of course, here the cardinality of vertex set is 5 and cardinality of edges, there are 6 edges, right? In fact, for both the graphs, this is the true. There are five vertices and 6 edges, right? In both the graphs.
Yes, sir. But in second graph, we have one point which have only one connection, and there is no any
Correct,
point in
correct.
first.
So here the degree of E is 1 in H, right? Whereas G has no vertices of degree 1, right? No vertex of degree 1 in G. Therefore, G is not isomorphic to H. Not isomorphic to H. Right? So these two graphs are non-isomorphic. Now, I think I should tell you there is a package Naughty written by one Australian professor, which is quite useful for classification of graphs. So basically, one can ask, up to the isomorphism, how many graphs are there? So let me maybe show you something here. Let me show you the. Yes, up to isomorphism. Naughty is a program which is Naughty graph isomorphism program. It's a very useful program. So one can ask this question: how many graphs are there up to certain vertices? So you can count actually. So there is a data available at Bernard Mackay's homepage. He has done a lot of work actually. Especially in generating these graphs. I think there might be table available somewhere. See, Naughty is a program. So this is a quite popular program. And why this is useful? Because graph isomorphism problem turns out to be very useful for classification of various combinatorial objects. And in business, you do require this classification. Even, for example, in your machine learning case, or data classification, data science, or different places you require data classification, right? And so if data can be represented by a graph, and then you can apply graph isomorphism problem to classify. So one can ask, how many graphs are there with certain properties. I think, yeah, here is the data. Let me show you. So look at this. For 2 vertices, there are 2 graphs. For 3 vertices, there are 4 graphs. All of them are here. Okay, so I think it is downloaded in some form, but okay, I need to probably show you the text. Oh, so this is in the form of notation, so you will not be able to know those things unless you look at the notation. Anyway, I think anyway, all are in this special form. So you need to, I was thinking that I can show you the specific graphs. But anyway, so you can see these are the simple graphs and how many of them are there. And you see up to 10 vertices, there are so many. Up to 11 vertices, this number is quite big. And as the number of vertices increases, this is very, very large. So in fact, as I told you, the online encyclopedia of integer sequence contains all the sequences. So 2, 4, 11, 34, 156, 1044, etc. If you enter, you can see how many graphs are there up to certain vertex. Is there any formula? You can actually check all that on online encyclopedia of integer sequences. So I give it as an exercise for you to actually go and check that. Whether how many graphs are there up to isomorphism, right? So data format page is here, where you can see how the data is formatted. So you can look at it. It's an exercise for you, and this is very, very important because this is very useful data. And if you know a little bit programming, this NATI is written in C program, so you can actually write programs by modifying this NATI, and you can use the NATI for the data classification. So from practical aspects, this is very useful. For some of you who are doing projects, this is a very useful project if you can classify. For example, many RNA viruses, for example, this COVID, the COVID is COVID-19 is an RNA virus. So many of these viruses have secondary structure formation, and this secondary structure formation is represented through graphs. And there is one professor who is Tamar is her name. She has done a lot of classification of viruses using graphs. So if 2 graphs are isomorphic, so that means 2 viruses are similar. So they have the similar properties. So you can classify the viruses. So plenty of applications in the real life actually. Okay, so graph isomorphism is very, very important. And till date, there is no polynomial time algorithm known for the graph class isomorphism problem. This is also another challenge for you. Okay. Any question at this point?
Sir, for this particular question, sir, sir, we can also interpret it this way, no, sir, that by means we cannot arrange the vertices in a way so that we get a graph similar to that in question. So that we can say that these 2 graphs are not isomorphic.
Yeah, so see, actually, it's easy to say that 2 graphs are not isomorphic if their degree sequence differ, right? So, for example, degree sequence means what? Degree of each vertex is number of edges it connects, right? So if I say that
Yes.
in one graph, the degree sequence is something, another graph it is different, of course those 2 graphs will not be isomorphic. Just in this case, degree of E is 1, whereas in the degree of E there is 3, right? So these 2 graphs are never isomorphic because there is no degree, may not be E, but maybe A or B, but there is no degree 1. So
Yes, sir.
reverse
Yes,
question
sir,
is easy.
understood.
Yeah, reverse question is easy,
Yes.
but actually, showing that given 2 graphs, whether they are isomorphic or not. So if there are, we need to find a polynomial time algorithm which will say that, okay, this is an isomorphic. That is a difficult problem. Okay.
Yes, yes.
Okay.
Sir,
Now I think, yeah.
Sir, in isomorphism, if 2 graphs have same number of points for degree 1, 2, etc., then we can also not we cannot say that both are isomorphic.
Correct. If the degree sequence is same, that doesn't mean that they are isomorphic. Very good. Yeah. So then we don't know actually, right? So we need to investigate more. That's why I'm saying
We
this is
have
a
to
very
check
nice.
connection.
Yeah, so you need to find, and this is an open problem. If you can work out a nice algorithm for telling that, there are some good algorithms now actually over the years, people have developed some good algorithms for finding when the two graphs are as an input. When we say that they are isomorphic, it's a very beautiful problem to work on. Actually, if you really want to work, this is a very good problem. In fact, one can also see whether we can find a polynomial time algorithm for quantum computer or quantum algorithm. That is also another interesting problem to look at. If you know a little bit of quantum computers, I think you can see these days you can learn from Qiskit, IBM Qiskit homepage. The textbook is there for quantum algorithms. You can learn easily, and then maybe you can develop the algorithm for graph isomorphism. If you can find a quantum algorithm, means you can find a polynomial time algorithm on a quantum computer. That will be an interesting problem to look at, actually, right? So that is also another very, very interesting thing to look at. Okay, so now I think I will talk about two more important concepts. One is known as circuit, or actually this topic is known as connectivity of the graph. So let me take an example. So here is a simple graph: A, B, C, D, E, F. A, B, C, D, E, F. Right. So we have base connected here. This is 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 connected here. And D and C is connected here. Right. This is a very simple graph. It's a simple graph. I can study some nice concepts known as path. So I can see that starting from A, D, C, A, D. So A, D, C, F, E. A, D, C, F, E is known as a simple path. Right. So what is path actually? So path is basically a path of certain length from one vertex to other vertex in the graph G is a sequence of edges. Right. So for example, here the sequence of edges is A, D, right? Then D, then D, C, then C, F, and then F, E, right? These are the edges: 1, 2, 3, 4, 4 edges. So this is simply a path. This is a simple path, right, of length 4, because it has 4 edges, right? This is a simple path. If I ask whether D, E, C, and A, is it a path? I ask you as a question: is it a path? D, E, C, and A, is it a path?
No,
No,
sir,
sir.
because
No,
the vertex, there is no vertex connecting E and C.
Correct. No, it is not a path. Right? Not a path. Very good. Okay. Another interesting thing to note: if I say that B, C, F, E, B, what does this B, C, C, F, E, B? Starting from B, then E. So I am writing, say, so B, then E, then F, then E, and then B. What is this?
So it is a cycle.
Cycle, or I would call it as a circuit, right? Circuit of length 4, right? Good. Or cycle, fine. If I look at another example, A, B, E, D, A, B. This is a path that is not simple. Why it is not a simple path? Because the edge AB is twice here, right? So you see AB and AB is there twice, right? So this is not a simple path. All these things you can really do, in the graph. So a graph is said to be connected if there is a path between every pair of distinct vertices of the graph, right? So then we say that the graph is connected. If there is a broken, if there are two parts of the graph, then we say that the graph is disconnected. This is very simple connectivity issue. Now, I think I'm going to talk about two kind of circuits. One is known as Euler circuit and Hamiltonian circuit, or Euler path or Hamiltonian path. Those are very, very important. And actually, as I should tell you, there was this Konsberg reverse bridge problem through which graph theory started, and Euler solved it, using a multigraph. So I'm not going to give you those historical details. By the way, if you want to read more about the graphs, Frank Harare, is a very good book on graph theory. Very good book if you want to read more. Okay. So Frank Harare is I think he has written around 1600 papers, in his lifetime. Even after his death, papers were coming. Because graph theory has a wider applications, right? You look at a problem in electrical engineering, you will find graph theory. You look at a problem in communication, you will find graph theory. You look at a problem in biology, you will find graph theory. You look at a problem in rail network, you will find a graph theory. You look at a problem in airport network, you will find a graph theory. It's a very, very useful thing. Whenever there is a network, there is a graph, right? And once there is a graph, you can study various properties, right? And try to infer some useful thing, try to do some useful thing in there, So what is Euler circuit? I should mention what is Euler circuit. You saw an example of circuit, right? Euler circuit. I call it as EC, Euler circuit. So in any graph G, which is simple graph, right? So it's a simple circuit containing every edge of G, right? And similarly, an Euler path in G is a simple path containing every edge of G, right? If it is not a complete cycle, then it is of course a simple path. So let us take an example here. So every edge should be exactly once, So you see there is this example A, B, C, D. Okay, and we have this here, this picture here, this picture here, this picture here, this picture here. This graph is G1. Now I can say that. So is there any Euler circuit here? A, and this is E actually. Yes. Any question? So A, E, C, D, E, B, A. Starting from A, E, C, D, E, B, A. We are covering every edge exactly one, right? And we are coming back to A. So this is an Euler circuit, right? If I look at this, A, B, C, D. So here we have here E. So this graph G2 has no Euler circuit, right? So you can see that you cannot find a Euler circuit here. So this is a important problem, right? So there is a result which I would like to mention here. One theorem given by Euler. A connected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. This is a very important theorem when you are asking whether you can draw these kind of pictures. For example, this kind of picture, can you draw this kind of picture without lifting a pen? Right? So this result relates here, right? Because here the degree is odd here, right? Degree is odd here. So this is not possible, right? So a corrected multigraph with at least two vertices has an Euler circuit if and only if each of its vertices has even degree. Okay. So this is something interesting result. Yes.
Sir, means all vertices should have even degree. Right?
Correct. Yes.
But sir, if two vertices have odd degree, then also it is possible to draw a graph without lifting pen. So
no, that is not possible actually. You can try. So I think it's a very good question. If you think that is a possible, try to construct a graph like that and see if it is possible or not. Right? It's just a pen of. You just require a pen, a piece of paper, a pen, and a cup of coffee, right? Or tea, whatever you like. What do you like, tea or coffee?
nothing, sir.
Nothing. Okay. Just basically, when you want to do math, you have to just sit down with tea and coffee, and things are done. Anyway, so this is a nice result. I would like to now give you the other part. So this is known as Euler circuit. Euler circuit, when we cover every edge exactly once, right? But what about there is another thing known as Hamiltonian path. Hamiltonian path, Hamiltonian path on circuit, So actually, let me draw a picture here, So let us take an example here. A, B, C. I can put another vertex here, B, E, and then we connect it here like this. This is a graph. So what is Hamiltonian circuit? So remember, there every edge was included. Simple Euler circuit is a simple circuit which contains every edge of G. Here, we require every vertex should be covered exactly once. So Hamiltonian circuit. Okay. A simple circuit. Right. Simple circuit that passes through every vertex exactly once. Okay, every vertex is important. There it was edge, here it is vertex. So I can ask whether this graph G has any Hamiltonian circuit. Yes, the answer is A, B, C, D, E, A. Right. I'm just worrying about the vertex. A, B, C, D, E, A. So Hamiltonian circuit. Right? What about this graph? A, B, C, D, G, E, F. This is our graph. Is this graph? Does this graph has Hamiltonian circuit?
No,
or Hamiltonian path? No. Very good. So no Hamiltonian circuit, no Hamiltonian path. So I think you understood the concept of Hamiltonian path and Hamiltonian circuit, right? So I think, yeah.
Sir, no point should have degree 1 in Hamiltonian circuit.
Well, actually, if G is a simple graph with n vertices such that the degree of every vertex in G is at least n by 2, then G has a Hamiltonian circuit. There is a result which I would like to mention here as a theorem, as you see. If G is a simple graph with n vertices such that degree of every vertex in G is at least n by 2, then G has a Hamiltonian circuit. By the way, this Hamiltonian circuit problem was the problem. It's a very difficult problem, you know. It was solved by Edelman using DNA computing. So he invented DNA computing. He took a 7 city 7 vertex problem, and and try to find a Hamiltonian circuit into it using purely DNA in the wet lab, and this is something sometime I can talk about it. It's a very beautiful result, because I teach DNA computing as well, so I know the result, and so I can tell you sometime. But yeah, it's really very interesting result,
So, sir, if
yeah.
a point have degree less than n by 2, then it cannot be Hamiltonian circuit. Right?
Yeah, so I think then you just try to construct. See, that's a beautiful thing in graph theory. If you once you get an idea, okay, sometime what happens, you get an idea, okay, this should be true, but when you try to do it by pen and paper, then you realize your mistake also sometime. So I think I invite you, if you think that there is some kind of characterization you are feeling, just try to construct an example, and see what happens. So I leave it as
a cyclic graph for,
yeah. So
means they can have degree less than n by 2, but still can be called a Hamiltonian circuit.
Yeah, no, just try and work it out, the example. You can discuss this on the WhatsApp anyway. I think I leave that up to you actually, because these are some important questions that will come into your mind. I think that's all for today. In the next class, I'm going to discuss about trees, and finally I will apply tree to a very popular problem known in data compression known as Huffman coding. Have you heard of Huffman coding? It has been taught to you, right?
Yes.
Yes, sir.
Yes, sir.
Okay.
In source
So you
coding.
already know about the trees as well, right?
Yes, sir.
Yeah.
So probably you will teach me when I'll discuss that, right? So let us discuss this in the last class on Wednesday, 8:30 in the morning. I think I've already made one part of the question paper for you, and I think Professor Rahul Muthu is bringing another part for you. So probably your question paper will be ready pretty soon, and we will see you. Probably exam is on 9th of July, right? If I am not wrong. And by the way, your project submission is of 7th July. So if you want to discuss anything before that, that is fine. You can discuss with us on WhatsApp. Please do use WhatsApp. I think nobody is using WhatsApp anymore. I don't see any discussion going on. Earlier, there used to be a lot of discussion in the WhatsApp group. People were asking a lot of questions. So either you people are, busy with some other work, or tired, or maybe doing competitive coding. I don't know actually, or maybe there is some health issues with some of you. But anyway, try to find some time and discuss these things, among yourselves. So I think that's all. So after trees, I will, we will end the course actually. I think that's all for this year. Okay. So for the project, you should also try to think in terms of any commercialization if it is possible, because if you think that there is a possibility of commercialization, you can create a startup out of it. Please do contact me. I will be able to support you in that direction. If you have any questions, please do ask.
Sir, in circuit, we should again end at the same point.
Yeah.
Where we started.
Whatever is this, yeah, where you started, you have to come back to the same point. Yes.
Okay. And sir, in bipartite graph, we can say that 2 points are same side of bipartite graph if and only if number of edges between them is even.
No, so basically in case of bipartite graph, you see we are partitioning the graph in two sets of vertices such that within a one group of vertices, no two vertices are connected. So if they are connected, then it's no more a bipartite graph, right? In either side. So that is very important to keep in mind. So whenever we are making this partition, then one vertex in one set is connected to other vertex in other set, not in the same set. That is an important thing to remember. Okay.
Yes, sir. But if we consider path from one point to another point, both points are in same side, then we can say that that path should have even
if they
number
are
of
on the
edges.
same, no. So basically, what I'm saying that it cannot be possible, right? That two vertices in the same set are connected, right? That is not possible in bipartite graph.
Sir,
Suppose,
not directly connected, but via other points. Means there exists some path between 2 points, including points on other side, which in that path number of edges should be even. That's what I am saying.
I mean, so again, I'm saying that you are also trying to get a result or theorem. So just try to prove it. So either try to prove it or try to find a counterexample to your statement. So which is very good. I mean, you are getting some nice ideas that this result should be true, because actually graph theory is such a simple subject. Many people think that it's very easy to do research in that, and indeed it is true actually. In reality, it is very easy to do research in graph theory. But sometimes some simple problems are difficult to solve. For example, graph isomorphism is such a simple problem, but still we don't know how to solve it in polynomial time. So what I'm saying that you try, so once you try and see if your statement is true or not, right? And if you can prove it, then it's established result. And otherwise, if you will find a counterexample to your statement, right? So just do it yourself, okay.
Okay, sir. Thank you.